Welcome back. In the last video, we looked at arrays. Arrays are great, but they have some disadvantages. For one, they can't easily change size. Although, in the last video we saw that by doubling the storage size on reallocation, we can achieve constant adding time in the long run. The second issue, which isn't as easily solved, is sparse storage. If we have indexed elements spanning a large range, then an array allocation will use much more space than necessary to hold blank space for missing indices. So let's say, for example, we have object 1 and object 1 million and that's it. An array would have to store 1,000,000 elements. This is a bit of a problem. The focus of today's video is the linked list. A linked list is made of nodes. Each node holds some data and a pointer to the next node. The list itself simply stores a pointer to the first node. After setting up the constructor, our first task will be to add an item to the list. For this simple example, I'm going to be adding to the front of the list. However, for an extension exercise, you can modify this code to add at any position. Hopefully the comments are self-explanatory enough. We can see from the code that this will be a constant time operation. As the length of the list grows, it isn't going to take any more time than usual to add an element. The next thing we're going to do is find the size of the lists. How could we do this? One strategy is to manually keep track of the size with another variable and manually adjust it on inserts and removals. This is probably the best strategy as it has a constant time, because we'll just be looking up a variable and returning it. Another strategy, which we're going to look at, is to search through the list and count the elements. We can see here that this implementation has big O n time complexity. That is, the time to execute varies linearly with the list length, since the whole list has to be counted each time. As a quality of life improvement, let's add a display function. This will be useful later when we're debugging the implementation. It'll use a pretty similar pattern to the size function we just made. Now let's remove a node. This function will remove a node, returning its contents. It's important to note that we are using a deep copy initializer to initialize removed data, because the removed node will be deleted and we can't have a shallow copy referencing that. That will throw an error. Anyway, again, this will remove from the front by default, but can be extended to remove from any position. Finally, we need to free memory on destruction. This will be a little trickier. We grab a node, work out the next node on the list, then delete the current node that we grabbed. We just need to be careful with the order of operations. It doesn't make sense to delete a node first and then look at its next element. That's all the code for the linked list done. We can now write a basic program to test it. And that's it. So I hope you enjoyed linked lists. There are many extension exercises we could do here, such as the ones that I mentioned. If you want a challenge, try reversing a linked list. That is, using this structure that we have right now, looping through and reversing. I'll leave that to you to work that one out. But anyway, all the best. Thank you for watching. Hope you had fun, and see you in the next one.